Imagine a world where light is simply a mystery, a phenomenon that fills our skies, colors our world, yet remains an enigma to the finest minds. For centuries, humanity believed light to be an intangible flow, a divine gift. But as science sharpened its gaze, a deeper structure began to reveal itself: hidden vibrations, invisible orientations, what we now call polarization. This is the story of how we uncovered one of the most elegant secrets of light.
The journey begins in the 17th century, when Christian Huygens, a Dutch physicist, proposed the wave theory of light, stating that light travels as a mechanical wave, similar to sound. Mechanical waves require a medium to propagate, so Huygens assumed the existence of a hypothetical medium called the luminiferous ether. According to Huygens, ether is weightless, elastic, transparent, and present everywhere, even in a vacuum. It serves as the medium through which light waves travel. His revolutionary wave theory of light explained phenomena like reflection and refraction, but it left open a deeper question: what exactly oscillates in a light wave?
In 1887, this view was challenged later by the Michelson-Morley experiment. The experiment attempted to detect the presence of the luminiferous ether by measuring differences in the speed of light as Earth moved through it. If ether existed, light should travel faster in the direction of Earth's motion through the ether, creating a measurable shift in interference patterns. No such shift was observed. The speed of light remained constant in all directions. This null result contradicted Huygens' idea that light needs a medium to travel. It strongly suggested that ether does not exist, paving the way for Einstein's theory of special relativity, which treats light as not requiring any medium.
While these experiments hinted at the nature of light, it was James Clerk Maxwell, in the 1860s, who provided the full theoretical framework. Maxwell's electromagnetic theory of light described light as a transverse electromagnetic wave, with electric and magnetic fields oscillating perpendicular to each other and to the direction of wave propagation. The answer started to unfold in 1808 when Etienne Louis Malus, a French engineer, made a chance observation. While studying light reflecting off the windows of the Luxembourg Palace in Paris, Malus noticed something peculiar. When he viewed the reflected light through a calcite crystal, the brightness changed depending on the crystal's orientation. This was astonishing. Ordinary light showed no such behavior. Through a series of careful experiments, Malus formulated what we now call Malus Law, which mathematically describes the intensity of polarized light transmitted through a polarizing filter.
James Clerk Maxwell proposed electromagnetic wave theory. According to this theory, light is an electromagnetic wave. It consists of vibrations of electric field and magnetic field in a direction perpendicular to the direction of propagation. Also, the vibrations of electric field and magnetic fields are confined to two different planes that are mutually perpendicular to each other. It was proved that electric field vibrations are only responsible for vision, therefore vibration of light means electric field vibrations. Electromagnetic waves are produced by excited atoms. A particular atom may produce electric field vibrations in any random direction. Thus, different atoms of a material can produce vibrations in a variety of directions. Due to this, a common source of light, like incandescent bulb or fluorescent lamp, will emit light due to the electric field vibrations in all directions. This type of light beam, which has vibrations in more than one plane, is called unpolarized light. Similarly, a light beam which has vibrations in only one plane is called polarized light.
Polarized light has vibrations restricted to a single plane. To study this, we use a device called a polarizer, a material that allows only vibrations along a certain direction to pass through. The pass axis of a polarizer is the direction along which it permits the electric field oscillations. The electric field vectors in the unpolarized light can be resolved into vertical and horizontal components. When unpolarized light passes through a polarizer, only the component of light oscillating along the pass axis emerges. As a result, the intensity of light is halved. Now suppose we place one more polarizer in front of the polarized light. This second polarizer is known as an analyzer. When the axes of the first and second filters are aligned, then all of the polarized light passed by the first filter is also passed by the second filter. The intensity will remain the same. I0 by 2. If the second polarizing filter is rotated, only the component of the light parallel to the second filter's axis is passed. When the axes are perpendicular, no light is passed by the second filter.
When unpolarized light passes through a polarizer, only the component of light oscillating along the pass axis emerges. I0 is the intensity of the incident unpolarized light. Now the light emerging from one polarizer is passed through a second polarizer called an analyzer. If the angle between their pass axes is theta, the transmitted intensity I depends on the cosine of the angle. Intensity is equal to I0 cosine square theta. This is Malus Law. Let the electric field amplitude of polarized light be E0. After passing through the analyzer, only the component E0 cosine theta passes through. Intensity is directly proportional to the square of electric field amplitude. Thus, rewriting again this equation. So, the transmitted light depends on the square of the cosine of the angle between the two polarizers. Malus Law beautifully explained why Malus saw variations in brightness when he rotated the crystal.
Building on this, Sir David Brewster in 1815 explored how polarization could occur naturally when light reflected off surfaces. He discovered a precise angle, known as Brewster's angle, at which reflected light becomes perfectly polarized. Brewster's law states tan theta b ton n2 by n1, where b is Brewster's angle and me1 and n2 are the refractive indices of the two media. This discovery not only explained glare off water and glass, but also had deep implications for optical technologies.
Thus, from Huygens wavefronts to Malus experiments, Brewster's reflections, and Maxwell's field theory, the story of polarization unfolded. A stunning realization that light was not just a wave, but a structured wave. Today, the understanding of polarization is vital in technologies like sunglasses, photography, and even quantum communication. Yet, it all began with a few curious minds noticing small anomalies in nature. Glints on glass, shimmering reflections, and crystals splitting light into strange patterns. Polarization teaches us a vital lesson. Sometimes, the universe's deepest secrets lie hidden in plain sight, waiting for someone to look a little closer.